further illustrate this four-step process, which I'm proposing can be used to solve any related rates problem, let's look at another variation of a rectangle problem we have solved in parts 1 and 2. The length of a rectangle is decreasing at a rate of 5 centimeters per second, while the width is increasing at a rate of 3 centimeters per second. We want to find the rate of change of the diagonal this time. Before, we found the rate of change of the area and the perimeter. Now let's find the rate of change of the diagonal with respect to time when the length is 10 centimeters and the width is 8 centimeters. I'll also point out that previously I just said, say, find the rate of change of the area when the length is 10 centimeters and the width is 8 centimeters. It was understood that I was wanting the rate of change of the area with respect to time, but perhaps it's clearer if I say that explicitly. So we first, as we've been doing, we write the rate in the problem, each rate as a derivative. So 5 centimeters per second, that's negative 5 centimeters per second, and that's the rate at which the length is decreasing. So the length is decreasing, so that's why the rate's negative. And the 5 centimeters is length, and the seconds is time, so that's the rate of change of the length with respect to time, dl dt. The derivative of length with respect to time is negative 5 centimeters per second. Another rate in the problem, 3 centimeters per second. That's the rate of change of the width with respect to time. So that's dw dt, which is positive since the width is increasing. And this time I want to find the rate of change of the length of the diagonal with respect to time. So let me use capital D to be the diagonal. Okay? Identify the dependent variables from the derivative notation in step 1. So L's a dependent variable, W is a dependent variable, capital D is a dependent variable. The independent variable here is time. Now, we need an equation that relates the dependent variables L, W, and D. Well, what's our shape? It's a rectangle. Length, width, diagonal. So I need an equation that relates L, W, and D. Well, this should remind me of the Pythagorean theorem, because D is the hypotenuse of a right triangle, L and W are legs. When a diagonal cuts a rectangle into two congruent right triangles. So Pythagorean theorem would say D squared equal L squared plus W squared. Step 3, take the equation in step 2, which is D squared equal L squared plus W squared, and differentiate both sides of it with respect to the independent variable time. So take the derivative of both sides with respect to time. Now, some people solve for D. In other words, they say D is the square root of L squared plus W squared first. You can do that, but then the derivative involves square root of a function. You end up with a composite function. The differentiation is just harder. There's really no need to solve this for D, to take the square root of both sides. We'll just differentiate both sides of this equation with respect to time, kind of like we do in implicit differentiation. Now, I have to remember here that D is a function of time, and L is a function of time, and W is a function of time. So the derivative with respect to d of d squared would be 2d, but I want the derivative of d squared with respect to t, where d is a function of t. So this d squared is really a composite function. You have an inside and outside. The derivative of the outside is 2d, but then the derivative of the inside is this. Just use chain rule. The derivative of the outside is 2d. The derivative of the inside is derivative of d with respect to t. Derivative of sums, the sum of the derivatives. The derivative with respect to t of L squared is 2L. That's the derivative of the outside, but I got to multiply by the derivative of the inside, dl dt. The derivative with respect to t of w squared is the derivative of the outside is 2w, but I've got to multiply by the derivative of the inside. That's chain rule. So I end up with an equation that relates the rates or the derivatives in the problem. Again, the derivatives in the problem were dl dt, dw dt, dd dt, and this equation relates those three derivatives. Now, I just see some easy algebra. Can't I divide both sides by 2? Let's make our equation as simple as possible. I do not have to do this, but if there's an obvious way to simplify the equation, let's just do that. I can divide both sides by 2. Step 4, substitute values into this equation and solve the equation for the requested derivative or rate, which is the derivative of the diagonal with respect to time. So I'm going to take my equation and substitute the known values. Well, do I know the value of d? Do I know the value of d? Well, I know the value of L, right? Now, I need to emphasize the following. This equation shows the relationship between these derivatives at any instant in time. The instant in time that they're wanting me to find the derivative of the diagonal with respect to time is the instant in time they're wanting me to evaluate that is the instant in time when the length is what? 10 centimeters and the width is 8 centimeters. If they gave me another value for the length and the width, I could plug those in here. In other words, this answer, the derivative of the diagonal with respect to time, the rate of change of the diagonal with respect to time changes over time, but it's always computed using this equation. So they don't tell me what D is, but I can figure it out because L is 10 and W is 8. So I've got a rectangle, and L is 10 and W is 8. And by Pythagorean theorem, the diagonal squared is 100 plus 64, right? So that would tell me the diagonal is the square root of 164. Centimeters, right? The diagonal is going to be in centimeters. So square root of 164 centimeters, I'm plugging that in for D, times the derivative of D with respect to T, that's what I'm trying to find, equals the length. What's the length? 10 centimeters. What's the derivative of L with respect to t? Minus a negative 5 centimeters per second. The width, they tell me, is 8 centimeters. And I know that dw dt is 3 centimeters per second. So now I want to solve this equation for the derivative of d with respect to t. So ten times negative 5 is negative 50, plus 8 times 3, negative 50, plus 24 is negative 26. Centimeters times centimeters per second would be centimeters squared per second. But then I'm dividing both sides by square root of 164 centimeters. Again, I'm solving this equation right here. I'm solving this equation. Solving this equation for the derivative of the diagonal with respect to time. So I compute what's on the right-hand side, and I get negative 26 square centimeters per second. I divide both sides by square root of 164 centimeters. So that turns out to be negative 26 over the square root of 164 centimeters per second. And you know, some instructors might want you to rationalize the denominator. Others might be happy for you to give a decimal answer. I'm okay with this answer, but it can be algebraically simplified a little bit, because I can rewrite the square root of 164 as the square root of 4 times the square root of 41. And then the square root of 4 is 2. So that turns out to be negative 13 over the square root of 41 centimeters per second. So notice that the diagonal of this rectangle is getting smaller, because the derivative of the length of the diagonal with respect to time is negative.